roughly about 44 grams per mole. But if you look at the boiling point for propane is 231 Kelvin. Boiling point for acetaldehyde, 294 Kelvin. Molecules of similar size have completely different boiling point. Well, what does that indicate? Well, explain the difference in the boiling point there. One molecule is polar, the other molecule is nonpolar. So there is a stronger interaction between the polar molecules, meaning the molecules of acetaldehyde will be attracted to one another with a stronger, we will have a stronger interaction there, resulting in a higher boiling point. Because when you're trying to boil the liquid there, you are trying to convert them from liquid into gas. Well, if it requires more energy, that means the molecules are being held together stronger than the one with the lower boiling point and requires less energy there. And this molecule is nonpolar. Why is it nonpolar? When you draw the Lewis structure, you will see. Okay, and that will be the Lewis structure for propane there. When you look at each carbon, carbon-hydrogen bound is nonpolar. Carbon is 2.5, hydrogen 2.1, 2.2. The difference is 0.3, 0.4, less than 0.4, equal or less than 0.4. The bound is polar. The bound is nonpolar. So each carbon-hydrogen bound is nonpolar. As a result, the entire molecule is nonpolar. Where when you have acetaldehyde and you have CH3, okay. Now this is the structure of the Lewis structure of the acetaldehyde. Now this part of the molecule is nonpolar, but when the carbon-oxygen double bond is involved in here, this is actually, there you have an unsymmetrical structure there. This part will bear a little bit more negative charge. This part will bear a little bit more positive charge, resulting in the entire molecule being polar. As a result, this particular molecule will have, this particular compound will have a higher boiling point. Okay, so this is what we use dipole-dipole interaction, one type of intermolecular force to explain why molecules of similar size have different boiling points. Well, the polar molecule requires more energy to separate, to get them into the gas phase, okay, and versus the nonpolar molecule there. So only polar molecule will experience what we call the dipole-dipole interaction. If you have a nonpolar molecule, there is not even a dipole there, and so there's no dipole-dipole interaction. Okay, now the question that we can ask you here is that which of these following chemicals will have dipole-dipole interaction here? Well, you look at the polarity of the molecule. Nitrogen, N2. Each nitrogen has the same ability to give or take electrons from one another. So N2 is a nonpolar molecule. Carbon tetrachloride. Now carbon tetrachloride, and if you look at that formula, if you look at that structure there, we are talking about a tetrahedral structure. We'll just draw the Lewis structure there. Perfectly symmetrical. Now carbon-chlorine bound may be polar, but if you have a perfect symmetry here, so carbon tetrachloride is nonpolar. Carbon monoxide, carbon-oxygen bound is polar. Diatomic molecule, when you have a polar bound, you have a polar molecule there. So among these three molecules there, only carbon monoxide is polar, has a permanent dipole. So nonpolar, they will not have dipole-dipole interaction. Nonpolar, they will not have dipole-dipole interaction. Carbon monoxide is polar. So this compound, the only compound that will exhibit dipole-dipole interaction is the molecules of carbon monoxide will interact with one another through dipole-dipole interaction. Okay, so this is what we're what we can use the different types of intermolecular forces involved in different types of molecules. There, this is the type of question that we would ask you in homework assignments there. And again, it's something that if you spend some time and work on the questions here, it's something that you will see in the homework assignment there, and you need to be able to answer these type of questions there. Okay. Now another type of question there is that when we look at molecules, a bromine molecule, okay, Br2 versus iodine chloride, molar mass is about the same, 162 versus 160. We'll ask you which one has a higher boiling point. Now we know bromine is a nonpolar molecule because same type of atoms with one another, you have the equability of give or take electrons with one another. Now, iodine chloride, iodine is in group 7A. Chlorine is also in group 7A, but one is on the top, the other is at the bottom there. There is a difference in electronegatividity. Going from top to bottom, electronegatividity is decreasing, meaning iodine will actually bear a partial positive charge and chlorine will bear a partial negative charge. So in this case, we have a polar molecule versus nonpolar molecule. Nonpolar molecule has a boiling point of 59 degrees Celsius, and then polar molecule is 97 degrees Celsius, almost double. So the size are about the same, but the temperature is much, much higher. And we are talking about a 42 degree, 38 degree difference there. Okay, so this helps us understanding the polarity in molecules there, and will help us to explain the amount of energy involved, and when you try to convert a particular compound from liquid into gas there. So evaporation, condensation, these are the things involving energy. And if you try to get water molecule into the gas phase there, you have to supply enough energy to separate the water molecules. But water molecules are interacting with one another because water molecules are polar molecules. So in this case, evaporation, that's an endothermic process. And then condensation going from gas back down to liquid, that's an exothermic process. Okay. So it has something to do, the amount of energy requirement has something to do with the polarity of the molecule, and has something to do with incremental forces there. Now if you look at the general trend in terms of the molar mass versus the boiling point. Now in nonpolar molecules versus polar molecules, generally speaking, the higher the molar mass, the higher the boiling point. So these are a group of nonpolar molecules. Their molar mass going from 28 to 160. You can see the boiling point in Celsius, negative 196 to positive 59. So that's an increase. So as the molecule is getting bigger, there is a stronger interaction among the molecules there, resulting in an increased boiling point. And the same thing follows, same thing happens in the polar molecule. Going from 28 to 162, you see negative 192 all the way up to 97. Okay, so in general, if you're comparing nonpolar molecules, the bigger the molecule, the heavier the molar mass, the higher the boiling point. But if you're comparing between nonpolar and polar molecules always have a higher boiling point. So carbon monoxide, nitrogen, molar mass, both are 28. Well, there's not a huge difference there, but negative 192, negative 196, that's a higher difference there. Okay, this number is a higher temperature compared to negative 196. And as you can see, negative 88 versus negative 112, negative 62 versus negative 90, 97 versus 59. Okay. So as you can see, in general, we want you to remember this. In general, as the molar mass increases, if you're talking about nonpolar compounds, within the nonpolar compound, as the molar mass increases, the boiling point increases. And same thing happens in the polar compound. But if you're comparing two compounds, one is polar, the other is nonpolar, when they have similar